Hello and welcome to the first section of the course where we will get introduced to the Scala programming language. Scala is a new and exciting language that runs on the JVM. Scala's distinguishing feature is its ability to allow the user to write programs in a functional way. In this section, we will study some of the key aspects of Scala that we will use in the rest of the course. This section is going to be divided into the following videos. First, we will look at the functional combinators in Scala. Then, we will learn about Scala traits, classes, and objects. Then we will look at IntelliJ IDEA, we will use for an integrated development environment for this course. Then we will look at two important Scala libraries, the Breeze library for linear algebra and the Wisp library for plotting. The second section of this course. In this section, we will describe the important concept of exploratory data analysis. We are first going to look at a concise definition of the general supervised learning problem statement. Then we are going to look at the two main subproblems of supervised learning, regression and classification. In this section, you will be exposed to several unsupervised learning algorithms, including k-means clustering, mixture of Gaussians clustering, and principal components analysis, and how they can be implemented in Scala. In this section, we will learn about neural networks. First video, we will look at the feed-forward neural network model, which is also known as the multi-layer perceptron. In the next video, we will implement the feed-forward neural network model in Scala. Then we will learn about the restricted Boltzmann machine neural network model, which is used for unsupervised learning, and again, implement it in Scala. In this section, we will look at some other Scala frameworks for machine learning. The first framework that we will be looking at in this section is the Akka actor framework. We are going to use the Akka actor model to implement the k-nearest neighbors algorithm in Scala. We will introduce another Scala framework that can be used for machine learning purposes, called Apache Spark. Hello and welcome to the first section of the course where we will get introduced to the Scala programming language. Scala is a new and exciting language that runs on the JVM. Scala's distinguishing feature is its ability to allow the user to write programs in a functional way. In this section, we will study some of the key aspects of Scala that we will use in the rest of the course. This section is going to be divided into the following videos. First, we will look at the functional combinators in Scala. Then, we will learn about Scala traits, classes, and objects. Then we will look at IntelliJ IDEA, we will use for an integrated development environment for this course. Then we will look at two important Scala libraries, the Breeze library for linear algebra and the Wisp library for plotting. In this first video, we will introduce functional combinators, which are a fundamental part of the Scala language. Functional combinators are a very important part of the Scala language because they allow you to manipulate Scala collections like lists and sets and maps in a functional way. Later in the course, when we start implementing our own machine learning algorithms in Scala, we will be using functional combinators quite heavily. In this video, we will first describe what functional combinators are as well as some of their properties. Then we will present some of Scala's most common functional combinators like map, flat map, fold, and filter. Finally, we will demonstrate how these popular combinators are used in the Scala REPL. At a high level, functional combinators are higher-order Scala functions that are most often used to perform some kind of operation on a Scala collection. The core functional combinators that we will discuss are built into the Scala programming language, although you are free to create your own. Most combinators obey the basic functional programming principles of not producing side effects, although there are some exceptions to this, like the for each combinator. Scala programmers also love functional combinators because they allow for very clean and concise code. Let's discuss four of Scala's most common functional combinators: map, flat map, fold, and filter in the context of a list. The map combinator evaluates a function over a list and returns a list of the same size. Flat map evaluates a function over a list which produces a nested list which is then flattened. Fold evaluates a function over a list which simultaneously updates a separate accumulator variable. Filter applies a Boolean function over the elements of a list and returns only the elements of that list that evaluate to true. Even though we have been using the example of a list here, the functional combinators would work the same way on other data structures like a hash map or a set. Now let's give a short demonstration of these functional combinators in the Scala REPL. Let's begin with the following list, which contains the integers from 1 to 5. Now let's apply a map function to this list, which takes a function that adds 1 to each element of the list. As you can see, the result is the same list with each element incremented by 1. Now let's apply a flat map to the list. We will pass in a function that returns the element itself as well as the incremented element wrapped in a list. As you can see, the result is a flattened version of what the map would have produced. Finally, let's demonstrate a filter. Let's pass a function that only evaluates to true for even inputs. As you would expect, the result is only the even elements of the list. These are the basics of how to use functional combinators in Scala. We will see a lot of these in future videos when we start to implement machine learning algorithms in Scala. In this video, we learned what functional combinators are in Scala, as well as how they are used. In the next video, we will talk about Scala traits, classes, and objects, which are the building blocks for any Scala program. Hello and welcome to the third video of this section. In the last video, we discussed some of Scala's most commonly used functional combinators. In this video, we will discuss Scala's traits, classes, and objects, which are used to handle the problems associated with abstraction and inheritance when building large programs in Scala. In this video, we will explain what traits, classes, and objects are and when each one should be used. We will also go back into the Scala REPL and demonstrate their respective functionality. Traits in Scala are very similar to interfaces in Java. They are most commonly used to represent abstract entities that can have abstract fields and methods that must be implemented in entities that extend that trait. Having said that, there are some important distinctions between Java interfaces and Scala traits. For instance, Scala traits are allowed to implement their own concrete members. As you can see in this example trait, we have two methods, isSimilar and isNotSimilar. IsNotSimilar has a concrete implementation, but isSimilar does not. Also, Java interfaces and Scala traits handle multiple inheritance in different ways. Scala traits use a concept known as mixing in, which we will demonstrate later on. In Scala, classes and objects are very closely linked. Scala classes are very similar to Java classes. They can have their own member variables and methods. They can extend traits and other classes. In Scala, instances are created from classes using the new keyword, and the class name acts as the constructor, which can take parameters. In this point class example, we inherit the similarity trait. It has two constructor variables called xc and yc, and it implements the trait's abstract isSimilar method. Scala objects are classes that only have one instance. Objects are often used in place of a class in which no internal state is required. For example, a place to store a library of util functions. In Scala, you do not need to use the new keyword to create an object. You simply type the object name. Let's go back to the Scala REPL to see exactly how traits, classes, and objects work. Let's first define a trait that has two methods, one that is concretely defined and one that is not. Let's now create a class that extends this trait. As you can see, if we do not implement the trait's unimplemented method, then we get an error. So let's implement this method inside the class. So now if we instantiate the class as we've done here, we can use the method that was implemented in the trait as well as the method that we implemented ourselves in the class that extended the trait. Let's now define another trait with another concretely defined method. Now let's try to create another class that extends both of our traits. Again, we see an error because we must implement our first trait's unimplemented method. Let's do this the same way as before. After instantiating our new class like so, we can now use the concretely defined methods from both traits. This is called mixing in traits. Finally, let's take a quick look at Scala objects. Let's define an object that contains a val. To access this val, we simply need to type the name of the object without the new keyword, and we can access the val with the standard dot notation. The exact same thing can be done with a method inside an object as well. In this video, we discussed the main building blocks of all Scala programs, which are traits, classes, and objects. We also got to see how they worked in the Scala REPL. In the next video, we will discuss a popular Scala IDE called IntelliJ IDEA. Welcome to the fourth video of this section. In the last video, we looked at Scala traits, classes, and objects. In this video, we will discuss a popular Scala IDE called IntelliJ IDEA. An IDE is essential when developing large Scala code bases. It makes things like project structure, code completion, and type detection a breeze, which will greatly boost your productivity. In this video, we will discuss how to download and install IntelliJ IDEA, as well as how to create an example Scala SBT project. IntelliJ IDEA can be downloaded from www.jetbrains.com/idea/download. Click on the download community link to download the free community version of IntelliJ IDEA. The paid version contains web development and database tools which are not necessary for this course. Once you have downloaded IntelliJ IDEA, it is time to create your very own Scala SBT project. To do this, first open IntelliJ IDEA, then select Create New Project. In the New Project menu, select SBT and then click Next. Now you must specify your project name, the location of the project, your Java SDK, your SBT version, and your Scala version. Then click Finish. And IntelliJ will create an empty Scala project in the location that you specified. This might take a little bit of time. Once finished, you are free to code away on your very first Scala project. In this video, we introduced IntelliJ IDEA as our Scala IDE. We also showed how to download IntelliJ and create a sample Scala SBT project. In the next video, we will look at Breeze, a powerful Scala library that we can use for all of our linear algebra heavy lifting in our machine learning algorithms later on in this course. Welcome to the fifth video of this section. In the last video, we learned how to use the IntelliJ IDEA Scala IDE. In this video, we will discuss the Scala Breeze library for linear algebra. Almost all machine learning algorithms involve some kind of linear algebra computations, so a library that efficiently implements these operations is essential. In particular, we will discuss how to add Breeze as a dependency to a Scala SBT project. Once we have done this, we will demonstrate some example linear algebra computations that Breeze can perform inside our IDE. Breeze is a free open source library that you can find on GitHub at github.com/scalanlp/breeze. If you scroll down on the Breeze page, you will find instructions on how to add Breeze as a dependency to your SBT project. There are three main dependencies to add: the core Breeze library, the Breeze native library to enable fast BLAS implementations, and the Breeze Viz library for plotting. Then we simply copy this SBT code and paste it in the build.sbt file in our SBT project. Once we have done this, all we need to do is refresh SBT and the required libraries get pulled from Maven Central, at which point we are free to use Breeze however we want in our Scala project. Now that we have Breeze as a dependency, let's demonstrate some common linear algebra computations that we will be using later in this course. First, let's create a matrix data structure called a dense matrix. A common operation that we would perform on a matrix is a transpose. We can do this by applying the denseMatrix.t method on our matrix. Another common linear algebra operation is matrix multiplication. To demonstrate this, let's create a second dense matrix of the same dimensions. We can multiply these two matrices in an intuitive way by simply using the multiplication operator between the two dense matrix objects. Finally, let's demonstrate an element-wise operation between our two matrices. Let's try element-wise addition. We do this with the : operator. Now let's run these examples in our IDE. As we can see, the results are as we expect. In this video, we introduced the powerful Breeze linear algebra library for Scala, discussed how to add it as a dependency to our Scala SPT project, and also demonstrated some common linear algebra computation examples. In the next video, we will introduce another Scala library called Wisp, which is used for plotting. In the last video, we learned how to use the Breeze library for linear algebra. In this video, we will discuss the Wisp library for plotting. As we will see in later videos, plotting and visualization are essential tools for machine learning. In this video, we will introduce Wisp as our plotting library for Scala. We will discuss how to add Wisp as an SPT dependency in our SPT Scala project. And finally, we will plot a sample dataset to demonstrate Wisp's plotting capabilities. Wisp is another free open source Scala library that can be found on GitHub at github.com/quantifind/Wisp. Wisp allows you to plot your data in several different ways, including line charts, bar charts, and scatter plots. If you scroll down the page, you can see the SPT dependency for the latest version of Wisp. Just like with our Breeze dependency, let's copy this dependency and paste it into our build.spt file. Again, once we refresh SPT, we have successfully added Wisp as a dependency to our Scala SPT project. Now that we have Wisp as a dependency for our project, let's plot a sample dataset. Let's plot a small list of integers from 0 to 10 with a line plot from within our IDE. Let's now hit run, and a new window should appear that contains our line plot. An interesting feature of Wisp is the ability to zoom in and out within a plot. Congratulations! You just finished the last video in this section of the course. Let's take a look back on what we learned in this section. First, we learned about Scala's super useful functional combinators. Then we learned about how traits, classes, and objects are used in Scala. Then we learned how to set up our IntelliJ IDEA IDE. Finally, we learned about two important Scala libraries, the Breeze library for linear algebra and the Wisp library for plotting. In the next section of the course, about exploratory data analysis. Welcome to the second section of this course. In this section, we will describe the important concept of exploratory data analysis. Exploratory data analysis allows you to get a general sense of the dataset that you will later be attempting to model with a supervised or unsupervised machine learning algorithm. Welcome to the video on exploratory data analysis. In this video, we will look at some common descriptive statistics used for exploratory data analysis, including mean, variance, maximum, and minimum. Then we will look at some common visualizations for exploratory data analysis, including histograms and scatter plots. Descriptive statistics are values that can be computed from your dataset that summarize its general shape and structure. We generally want to compute descriptive statistics for each column or feature of our dataset. Perhaps the most common descriptive statistic is the mean, which is a feature's average value. However, the mean is not robust to outliers in the dataset, which is why the median is also a useful descriptive statistic. The median is the middle value by magnitude of the feature. The mode is another commonly used statistic, which is equal to the most frequently occurring value. The variance is another common descriptive statistic, which describes the spread of the data about its mean. It is also very important to know the complete range of values that your dataset can take, which is indicated by its minimum and maximum values. These descriptive statistics allow you to get a good idea of the overall shape and structure of the dataset that you are working with, which you cannot get by simply staring at the raw data. A scatter plot of two features in a dataset can also suggest important relationships. For example, in the left plot, there seems to be a strong linear relationship between the two features, which suggests that one may be a good predictor of the other in the context of a supervised learning problem. In the right plot, there does not seem to be a clear relationship between the two features, which would be very useful to know in the context of feature selection. Histograms are another very useful exploratory data analysis visualization. Histograms attempt to illustrate the general shape of the underlying distribution that your data points have been sampled from. To build a histogram, you simply segment the values that your data can take between its maximum and minimum. These are called the histogram's bins. Then you count how many data points fall into each one of these bins and plot the counts on a bar graph. A histogram is a great way to visually summarize a dataset. It can indicate various descriptive statistics such as mean and variance, as well as illustrate the modes or peaks of the data. In this video, we discussed exploratory data analysis in terms of descriptive statistics and visualizations. In the next video, we will look at how to actually perform exploratory data analysis in Scala using the Breeze and Saddle libraries. Welcome to the second video of this section. In the previous video, we learned about the concept of exploratory data analysis, including descriptive statistics and visualizations. In this video, we will actually implement exploratory data analysis in Scala using the Saddle and Breeze libraries. In particular, we will use Saddle data frames to compute descriptive statistics, and we will use Breeze to visualize histograms and scatter plots. Let's use the Boston housing dataset as our example dataset. The Boston housing dataset has 13 input feature variables and 1 output variable, which is the housing price in thousands. In order to use the Saddle library, we have to add this dependency to our build.spt file. Once we have added Saddle as a dependency, the first thing we want to do is represent our Boston housing dataset as a Saddle data frame, which has built-in methods to compute descriptive statistics. Saddle has a handy feature to read CSV files and convert them directly into data frames, but unfortunately the Boston housing dataset is a .data file rather than a CSV file, so we will have to take a few extra steps. The first thing that we're going to do is read our raw data file as a list of lists of doubles with this function. i.e., each example in our dataset is a list of doubles of length 14, where the first 13 elements are the input feature vector and the last element is the output. We then convert to a list of saddle vector objects, which we can then convert to a saddle matrix object, which we can then finally convert to a data frame. Now we can finally compute some descriptive statistics. Let's use the output variable of our dataset. We use the data frame's call@at method to select the particular feature. In this case, we want the 14th and last feature for the output variable. This creates a saddle series object from which we can compute our statistics. Let's compute the mean, median, variance, maximum, and minimum. When we run our code at the end of this video, we will see these outputs. Now let's plot a histogram of the housing prices using Breeze. Breeze does not know how to communicate directly with Saddle, so we first must convert the Saddle series into a sequence, which is a Scala collection. We can then plot the histogram of this data by simply calling Breeze's hist function, which we supply with our sequence, as well as a histogram bin size, which we choose to be 10. Finally, we want to be able to create scatter plots between each input variable and the output price variable in order to observe some potential causal relationships. In order to do this, let's create a 4x4 grid of subplots in order to show all 13 plots at once, and also our histogram plot. We then iterate over each input feature in our saddle data frame, convert it to a sequence, and then plot it in the appropriate subplot. Now let's finally run our code and observe our descriptive statistics, our scatter plots, and our histogram. So in the resulting plot, we can see our histogram for our price output variable, as well as our price output variable plotted in a scatter plot against the other input features. As you can see, some of them appear to be quite random, whereas some of them appear to have a linear relationship. We can also look at our descriptive statistics that we printed out. Here we see the mean, variance, median, maximum, and minimum of our output price variable. Congratulations, we just finished the second section of the course. Let's take a look back on what we have learned. First, we learned about exploratory data analysis and the importance of descriptive statistics and visualizations. Then we learned how to implement exploratory data analysis with Scala on real data. We used data frames from the SADA library to compute descriptive statistics and the Breeze library to create histograms and scatter plots. In the next video, we will begin our next section called supervised learning. Welcome to the first video in the supervised learning section of this course, where we will discuss the supervised learning problem formulation. In this video, we are first going to look at a concise definition of the general supervised learning problem statement. Then we are going to look at the two main subproblems of supervised learning, regression and classification. The intuition given in this video will be essential for when we actually start implementing supervised learning algorithms in Scala. Let's start with the definition of the supervised learning problem. Given a dataset D of xy tuples, where x is a vector of length n, which we call a feature vector, and y is a scalar valued target variable, supervised learning is the problem of finding a function f optimally maps feature vectors to target variables. The particular function f is determined by the particular supervised learning model being used. For example, linear regression, decision trees, or SVMs will each have their own definitions for what f is. Furthermore, the function f is generally learned from the dataset D by trying to minimize some kind of loss function, which is generally a function of the difference between f's prediction of the target variable and the actual value of the target variable. The reason why we care about the supervised learning problem is that if we could learn such a mapping function f, it would allow us to make predictions for new feature vectors that we see in the future. Clearly, this can have many real-world use cases, which we will mention in the next slides. The general supervised learning problem can have two special cases, when the target variable is continuous and when the target variable is discrete. When the target variable is continuous, the supervised learning problem is called regression. Some real-world examples of regression problems are predicting real-valued stock prices, predicting the weather tomorrow, or predicting energy consumption in a city. The other special case of supervised learning is when the target variable is discrete and can only take values from a particular set of classes. In this case, the supervised learning problem is called classification. For instance, the problem of trying to classify handwritten digits, where given a handwritten digit, you want to predict which of the 10 classes from 0 to 9 it belongs to. Or if you are given a set of documents and you want to classify them by a particular category, like application form, financial document, or email, etc. Classification is also commonly used in the context of medical diagnosis, where given a medical image, you want to determine whether or not a patient has a disease. In this video, we define the problem of supervised learning and also describe the two main subproblems of regression and classification. In the next video, we will explore two basic regression algorithms, linear regression and GLMs. In the last video, we introduced the general supervised learning problem and also the subproblem of regression. In this video, we will focus on two basic regression algorithms which we will implement in Scala in the next video. In this video, the two regression algorithms that we are going to cover are linear regression and generalized linear models, or GLMs. Linear regression is perhaps the most basic and well-known of all regression models. The key assumption in linear regression is that there is a linear relationship between the input feature vector and the output target variable. A linear regression model is fully described by a weight vector W, which is the same length as the input feature vector. An input feature vector is mapped to an output target variable by performing an inner product operation with the weight vector W. This operation is shown by the formula below. Therefore, training a linear regression model refers to the process of computing the optimal weight vector W that maps feature vectors to target variables. The optimal weight vector that we wish to compute is the one that minimizes the mean squared error between the predicted targets and the actual targets over the entire dataset. From the previous slide, we know that the predicted target is simply the inner product between the weight vector and the input feature vector. The squared error is simply the square difference between the predicted and actual values of the target variable given the weight vector. As you can see, the loss function L is a function of the weight vector. The weight vector that minimizes the loss function can be computed via standard optimization techniques, like taking the derivative of the function with respect to w and setting it equal to 0. We have left out the full derivation, but the optimal weight vector turns out to be the inverse of x transpose x times the product of x transpose and y, where x is the matrix of input feature vectors and y is the vector of target variables. This formula for optimal weight vector is sometimes referred to as the normal equation for linear regression. However, in many datasets, there is a nonlinear relationship between feature vectors and a target variable. In this case, linear regression, as we described it in the previous slide, would not be an appropriate model to use. However, you can still model nonlinear relationships in a linear fashion using basis functions. A basis function is a nonlinear, vector-valued function that is applied to the feature vector, i.e., a basis function accepts the feature vector as input and produces another vector that may or may not be the same length as the feature vector. Generalized linear models are similar to linear regression except for the fact that nonlinear basis functions are applied to feature vectors. There is still a weight vector w that needs to be learned, and a target variable prediction can be obtained by performing an inner product between the weight vector and the output of the basis function applied to the feature vector. So essentially, GLMs are linear with respect to the weight vector w, but nonlinear with respect to the feature vector. It turns out that the optimal weight vector has identical normal equations to that of the linear regression, except, again, the basis functions must be applied to the feature vectors. The following flowchart illustrates the training and prediction procedure for both linear regression and generalized linear models. In each case, we start with a training dataset of an input feature matrix whose rows are the input feature vector and the corresponding output vector. The training procedure amounts to computing the normal equations for the weight vector which we present for both models. Then, when predicting the output for a new input vector x star, we just apply the learned weight vector to either x star for linear regression or the basis function applied to x star for the generalized linear model. In this video, we learned how linear regression and generalized linear models work. In the next video, we are going to return to Scala and actually implement these algorithms. In the last video, we learned about two basic regression algorithms, linear regression and generalized linear models. In this video, we will actually implement these regression algorithms in Scala. First, we will cover linear regression's implementation in Scala, and then cover GLMs. We will implement linear regression as a Scala class. The class constructor arguments will be the training set that we will use to build our model. Specifically, it will be the matrix of input examples represented by a Breeze dense matrix object, and their corresponding outputs also represented by a Breeze dense matrix object. The third constructor argument is a function corresponding to the basis function being used for GLMs. Specifically, this is an option of a function, so the user has the ability to provide a basis function or not, in which case ordinary linear regression will be performed. When the class is instantiated, we immediately apply the basis function to the inputs if one is provided. We do this by pattern matching on the basis function option. Now let's look at the most important method in this class, the train method, which learns the linear regression weight vector. If we look at the bottom of this method, we can see the normal equation for linear regression that we explained in the previous video. We have implemented the normal equation using some of Breeze's standard linear algebra operators. However, there is one extra term in here, which is used for regularization. We will explain regularization in a later video in this section. The other method is the predict method, which takes weights that have presumably been learned using the train method and inputs to produce predictions. The number of predictions is determined by the number of input examples in the matrix passed in. And as we learned in the previous video, a prediction can be made by simply taking the inner product between the weights and the inputs, which we do here with Breeze's inner product operator. The last method that we will look at is the evaluate method, which is used to compute the performance of a learned weight vector on some test data. The method takes 4 arguments: the learned weights, the test inputs, the test outputs, and an evaluator function. The evaluator function takes the predictions and the actual outputs and compares them in some way to produce a scalar evaluation score. There are many possible ways a user may wish to evaluate the predictions, so we leave it up to the user to provide the particular evaluation function. This makes the evaluate method a higher order function. Now that we've implemented our linear regression class, let's actually use it on our Boston housing prices dataset. First, we import the dataset and transform the inputs and outputs to dense matrix objects. Then we create a linear regression object from the class we just created and call the train method on that object, which gives us the learned weights. Now let's evaluate the weights we just learned. For test data, let's just take the first 30 data points from our dataset. As for an evaluation function, let's use the mean squared error function, which is just the average squared difference between the predictions and the actual outputs. Now let's pass everything into the evaluate method. Let's now run the code and print out the mean squared error. As we can see, the average squared prediction error is about 9.5. In the coming videos, we will explore some more rigorous evaluation techniques involving regularization and cross-validation. In this video, we learned how to actually implement linear regression and GLMs in Scala. In the next video, we are going to move away from regression and take a look at 2 popular classification algorithms. In the last couple of videos, we looked at regression algorithms. In this video, we are going to focus on the other supervised learning subproblem, classification. As a reminder, classification is the special case of the supervised learning problem where the target variable can take values from a set of discrete classes. Specifically, in this video, we are going to look at 2 basic classification algorithms, k-nearest neighbors and naive Bayes. Let's begin with the k-nearest neighbors classification algorithm. The k-nearest neighbors algorithm is very conceptually simple, yet it can still be very effective in practice. Given a data set of training data, k-nearest neighbors predicts the target class of a new data point by searching through the data set for the k closest data points to the new data point and takes a majority vote over the corresponding outputs of these neighboring data points. For example, if the corresponding outputs of the 5 nearest neighbors to a new data point are 3 outputs of class A and 2 outputs of class B, then the new data point will be predicted as class A. Since this algorithm involves finding similar data points, it requires some kind of distance function. Euclidean distance is a common choice. The optimal number of neighbors k can be determined via cross-validation, which will be explained in detail in the next videos. The following flow chart illustrates the k-nearest neighbors classification algorithm. This algorithm is somewhat unique in that there is no real training phase. All computations are done at prediction time. When trying to predict the output for a new input vector, the predicted output is found by searching the training data set for the k closest input vectors according to the given distance function. Then the most common output class and the corresponding k outputs is given as the prediction. The second classification algorithm that we are going to look at is the naive Bayes algorithm. The naive Bayes algorithm is based on Bayes' rule from probability. Bayes' rule states that for 2 random variables y and x, the conditional probability of y given x is equal to the probability of y times the conditional probability of x given y divided by the probability of x. In Bayesian statistics, the probability of x given y is called the likelihood of x. The probability of y is called the prior probability, and the probability of y given x is called the posterior probability of y. The naive Bayes algorithm predicts the class y for a new input data point x by the class that possesses the largest posterior probability given the input data point x. So essentially, this amounts to computing the probability of a class y given an input x for each class using Bayes' rule, and then finding the maximum. From the formula for Bayes' rule in the previous slide, we see that the denominator, the probability of x, will be the same for each possible class y. Therefore, we can remove this from the argmax computation without having any effect on the final answer. Next, we use the naive Bayes assumption, which states that the elements of the input vector are conditionally independent given y. This means that we can factorize the likelihood into a product of element-wise likelihoods. Now all that is left is to estimate the likelihood elements and the prior probability of y from the data. For real valued inputs, it is often assumed that the likelihoods follow a normal distribution whose parameters can be computed via maximum likelihood. We will show an example of this in the next video, actually implement naive Bayes in Scala. The following flowchart illustrates the naive Bayes classification algorithm. At training time, the prior probabilities py for each possible class are learned from the training data. Also, for each possible class, the probabilities of each element of the feature vector are learned from the training data. Once this is done, prediction simply amounts to selecting the class that has the highest posterior probability, which is computed using Bayes' rule, which is a function of the probabilities that were learned at training time. In this video, we gained a good understanding of two commonly used classification algorithms, k-nearest neighbors and naive Bayes. In the next video, we will actually implement these algorithms in Scala. In the previous video, we introduced two commonly used classification algorithms, k-nearest neighbors and naive Bayes. In this video, we are going to actually implement these algorithms in Scala, as we have done previously with linear regression and GLMs. First, we will implement k-nearest neighbors, then we will implement naive Bayes and test them both on some actual data. Let's begin with the k-nearest neighbors implementation. We create a class called nearest neighbors with four constructor arguments. K, the number of nearest neighbors to include in the majority vote, the input example matrix, the corresponding output classes, and a distance function used to compute the nearest inputs. As we learned in the previous video, there is no training required for the k-nearest neighbors algorithm. At prediction time, we simply search through the dataset for the k closest data points and take a majority vote from their corresponding output classes. This is all done in the predict method, which takes a single argument corresponding to an input data point whose output class we want to predict. The first step is to compute the distances between the input data point in question and each of the example data points in the dataset. This corresponds to applying the given distance function to each row in the input matrix, which we can do via a map operation. Now that all that is left is sorting the data points by distance and taking the k closest points. We also make sure to record the indices of the data points via a zip with index operation in order to get the output classes corresponding to the k closest input points. Now the final step is to take a majority vote from the k closest output classes. That is, we determine which class in the set of k is the most frequent. One way to do this is to apply Scala's group by function while passing in the identity function, which groups each distinct class together within a map data structure. We then simply select the class corresponding to the largest group. Now let's test our k-nearest neighbor algorithm on an actual dataset. Let's use the UCI ionosphere dataset, which has two possible output classes. We import the dataset and transform the input examples into a dense matrix object and transform the outputs into a sequence of strings. Let's now instantiate the nearest neighbors class using the first 300 data points of our dataset. We also use the Euclidean distance measure as our distance function and set our k value to 4. Let's then test our implementation on the next 50 data points from our dataset and compute the accuracy by counting how many classes were predicted correctly. Now let's run the code. After we run the code, we see we get an accuracy of about 98%. Now let's implement our second classification algorithm, naive Bayes. Again, let's create a Scala class called naive Bayes, which takes two constructor arguments, a dense matrix of input examples and a sequence of strings corresponding to the outputs. If you remember from the previous video for naive Bayes, in order to compute Bayes' rule, we must compute conditional likelihoods of each input feature given a class. In this implementation, we assume that each input feature is normally distributed. Fortunately, Breeze provides a Gaussian distribution class that we can use here that will make things much easier for us. A Gaussian distribution is defined by two parameters, its mean and its standard deviation. We will use the maximum likelihood estimate of these two parameters, which is just the empirical mean, and the empirical standard deviation, which can be computed directly from the data. In order to do this, we first group our input data according to its output class using Scala's group by function. Then we compute the empirical mean and the empirical standard deviation for each input feature from the data points from each class, and with them create Gaussian distribution objects. In the end, what we're left with is a map data structure whose keys refer to the possible output classes and whose values are an array of Gaussian conditional likelihoods for each input feature given the class corresponding to the key. The next step is to compute the prior probabilities for each class. The prior probability for a class is simply the number of times that class appears in the training set divided by the total number of examples in that training set. We do this again using Scala's group by function, passing in the identity function. And then we perform the division with a map values call. At prediction time, we must compute the posterior for each class given the input vector and select the maximum as our prediction. We compute the posteriors for each class using a map function over each possible class. Within the map, we select the prior probability of the class from the pre-computed map data structure that we just explained. We also compute the likelihoods of each feature for the input vector using the Gaussian likelihoods for the given class that we also pre-computed. The Gaussian objects have a .pdf method which can be used to obtain the probability of a particular value for the given Gaussian distribution. Finally, instead of taking the product of probabilities, as we explained in the previous video, we instead take the log of the product, which is equivalent to the sum of the log products. We do this to prevent numerical instability, which can occur when multiplying many small probabilities. Finally, we simply take the class corresponding to the largest posterior probability as the prediction. Finally, let's test our naive Bayes implementation on the exact same dataset we used to test our nearest neighbors implementation. When we run the code, we can see that our naive Bayes implementation predicts about 78% of our examples correctly. In this video, we implemented two classification algorithms in Scala. In the next video, we will look at the concept of model selection. In the previous videos, we learned about several regression and classification algorithms. Now that we understand these supervised learning models, the next step is to learn how to evaluate them. This process is called model selection. In this video, we will first take a look at the important concepts of overfitting and regularization. Then we will look at the commonly used cross-validation evaluation technique. It is often the case with many supervised learning models that the model's performance on the dataset that it was trained on is significantly better than its performance on new unseen data. This is obviously a problem if you want to deploy your model in a production setting. Ideally, you would want your model to generalize well to unseen data. When this happens, it often means that the model that you trained is too complex. Specifically, it means that your model is so complex it is actually fitting to the noise associated with your training data rather than its underlying structure, and for that reason, the performance of the model will suffer. This phenomenon is called overfitting. In order to fix this overfitting problem, we need a way to control the complexity of the model at training time. This is called regularization. Regularization is a technique that enforces a complexity penalty on the model parameter that is being learned during training. Let's take the example of linear regression. We can measure the complexity of the weight vector W by simply taking its inner product with itself. We add this complexity term to the original loss function and scale it by a scalar term gamma. With this new loss function, we are trying to minimize the original loss function as well as minimize the complexity of the weight vector being learned. The gamma parameter determines the strength of the complexity penalty in the loss function. Now the remaining question is, how do we choose gamma? Generally speaking, we want the gamma parameter that results in the model that performs the best on unseen data. This is done through a process called cross-validation. Generally speaking, the way to assess a model's performance on unseen data is to make an 80-20 split in your training data and use the 80% chunk to train your model and the 20% chunk to test. This is a good strategy. However, you can imagine the case where the 20% you use for test does not happen to be very representative of unseen data in general. In this case, the test error would not give you a good idea of your model's generalized performance. A better strategy is to initially segment your dataset into k different chunks. This gives you k different training and test set pairs, where for each pair, one of the k chunks is used for testing, and the other k-1 chunks are used for training. Now you can perform the same process as before k times, each with a different training and test set, which results in k different test set performance values. The average over these values will give you a more unbiased estimate of your model's generalized performance. This technique is called k-fold cross-validation. Let's implement cross-validation in Scala as a way to choose the optimal regularization parameter gamma. We will do this as a method within the linear regression class. This method takes 3 input arguments: the number of folds to use, the regularization parameter, and the evaluation function. The first thing we do is we segment the dataset into a number of folds determined by the fold parameter. We do this with Scala's grouped function. Then we fold over the partitions, and we use the current partition as the test set and the rest of the partitions as the training set. We then train on the training set and evaluate on the test set and record the error in the accumulator. Finally, we take the average test error by taking the mean of the accumulator. Now let's use cross-validation to learn the optimal regularization parameter for our Boston housing dataset. We are going to vary the regularization parameter from 10 to the minus 6 to 10 cubed, incrementing by powers of 10 each time, and at each value we are going to perform 5-fold cross-validation. Then we are going to plot the resulting cross-validation errors for each regularization parameter value. If we run the code, we see that the regularization parameter that produces the smallest error is at 0.1, and therefore that is the value of the regularization parameter that generalizes best to unseen data. In this video, we learned about the overfitting problem as well as how regularization can be used to mitigate it. We also learned about how cross-validation can be used as an effective way to measure a model's performance on unseen data. This has been the last video in the supervised learning section of this course. In the next section, we will cover the unsupervised learning field of machine learning. Welcome to the fourth section of this course. In the previous section, we learned about supervised learning. In this section, you will be exposed to several unsupervised learning algorithms, including k-means clustering, mixture of Gaussians clustering, and principal components analysis, and how they can be implemented in Scala. But before we get into any specific unsupervised learning algorithms, we must first understand what unsupervised learning is. In this video, we will define the unsupervised learning problem and explain its two main subproblems, clustering and dimensionality reduction. The main difference between supervised and unsupervised learning is that unsupervised learning has no target outputs. It only deals with an input dataset. The general goal of unsupervised learning is to understand the structure of the dataset in different ways. For example, say you want to segment your dataset into natural groupings based on the similarities between data points. This is the unsupervised learning problem of clustering. Or say that you want to reduce the number of features that your dataset currently has. This is the unsupervised learning problem of dimensionality reduction. Also, it is important to note that the evaluation of unsupervised learning algorithms is much more difficult than with supervised learning, since we do not have any gold standard target outputs that we can measure against. Now let's focus on the clustering problem. Again, this problem deals with segmenting data points into natural groups that we call clusters. The general objective of clustering is to divide data points into clusters in such a way that data points are more similar to the data points within their cluster than to data points in different clusters. The diagram below shows three clusters identified by color. Each data point is closer to the data points in its own cluster than those of the other clusters. There are also many real-world examples of clustering problems, like clustering groups of customers in order to develop targeted marketing campaigns, clustering similar products together to help with recommendations, or even clustering users in a social network to identify communities. Some popular clustering algorithms are k-means clustering, mixture of Gaussians clustering, and hierarchical clustering, amongst many others. The other unsupervised learning problem that we will focus on in this section is dimensionality reduction. Dimensionality reduction is the problem of transforming your data set into one that has fewer features or dimensions while minimizing the amount of information being lost. Dimensionality reduction can be a handy tool for a number of use cases. For example, it is often used as a pre-processing step to remove redundant features from a dataset. Reducing the dimension of a dataset can also make it more manageable in terms of memory. Also, dimensionality reduction can be a useful tool for visualizing your data, since it is very difficult to visualize high-dimensional data. Some popular dimensionality reduction algorithms are PCA, ICA, and factor analysis. The diagram shown here is a reference to PCA, which finds the direction of greatest variance in your data and uses these directions as the new coordinates in a lower dimensional space. We will study the PCA algorithm in greater depth later in this section. In this video, we introduce the topic of unsupervised learning as well as the clustering and dimensionality reduction problems. In the next video, we will focus on our first clustering algorithm, k-means clustering, and we will also implement it in Scala. Welcome to the second video of this section. In the previous video, we defined the unsupervised learning problem of clustering. In this video, we will discuss our first clustering algorithm, k-means clustering. In this video, we are going to outline how the k-means algorithm clusters data points, and then we are going to actually implement it in Scala and cluster some of the actual data. But before we do that, we need to understand some k-means basics. First of all, it should be noted that k-means is one of the most well-known clustering algorithms due to its simplicity. It should also be noted that k-means only works for numerical datasets. So if your data is not numeric, you must transform it into a numeric format in order to use k-means. As input parameters, k-means requires the number of clusters to be found, k, as well as a function that measures the similarity between two data points. The algorithm learns these clusters via an iterative descent method. We will be using Euclidean distance as our k-means distance measure. The Euclidean distance between two vectors is simply the sum of the squared difference between the corresponding elements of the two vectors. K-means is guaranteed to converge with this distance measure. The k-means algorithm involves iterative computations of cluster means. The mean of a cluster is simply the mean of all the data points that are assigned to that cluster. The main goal of k-means clustering is to cluster the data points in such a way as to minimize the average distance between the cluster mean and the data points assigned to that cluster. In simple terms, this just means that the data points belonging to the same cluster should be as similar to each other as possible. The following is the pseudocode for the k-means algorithm. As you can see, the k-means algorithm iterates between two main steps: computing the cluster means, which we discussed in the previous slide, and assigning each data point to the cluster with the nearest cluster mean by Euclidean distance. The cluster assignments and the cluster means are randomly initiated, and the two iterative steps are computed until the cluster means stop changing, at which point convergence has occurred and we arrive at our final clusters. Now let's implement k-means in Scala. Let's start with the main cluster method. It takes the dataset as a sequence of dense vectors, the number of clusters to learn, and the distance function as inputs. Therefore, it is a higher order function. The first thing we do is randomly initialize our cluster means and cluster assignments with the initialize clusters method. We define a cluster with the cluster case class, which contains the cluster mean and the data points assigned to that cluster. We randomly initialize the clusters by randomly shuffling the data set, then grouping them into k groups with Scala's group function. We initialize each cluster mean with a vector of zeros. Now let's discuss the implementation of the two iterative steps in the while loop. The first step computes the cluster mean for each cluster. This is implemented in the compute mean function. In this function, we simply average the data points in each cluster using a fold. The other iterative step reassigns data points to clusters given the updated cluster means. This is done in the assign data points method. In this method, we use two nested folds. The outer fold traverses all of the data points and accumulates a map that maps cluster means to assigned data points. The inner fold traverses each cluster mean and accumulates the nearest cluster mean for the data point in the outer fold. In the end, we obtain the new cluster assignments and we convert the map to a sequence of the cluster case class. Now let's run our k-means algorithm on our 311 service request dataset. Specifically, we will cluster the noise complaints. After we have imported our dataset, we will instantiate our k-means object using that dataset, 6 clusters, and the Euclidean distance function. After our clusters have converged, we will plot them each with a different color. Let's run our code. It may take a few seconds for our clusters to converge, but once they have, you should see a plot that looks something like this. As you can see, the data points corresponding to each cluster are all closer to their own cluster means than the cluster means of other clusters. In this video, we have explained what the k-means algorithm is, how it learns clusters, as well as how it can be implemented in Scala. In the next video, we will look at a slightly more advanced clustering algorithm called mixture of Gaussians clustering that has several advantages over k-means. Welcome to the third video of this section. In the previous video, we looked at k-means clustering, which is a relatively simple clustering algorithm. We will look at a slightly more complex clustering algorithm, which offers a few advantages over k-means. In this video, we will first take a look at the general intuition behind mixture of Gaussians clustering. Then we will compare mixture of Gaussians with k-means clustering. Then finally, we will look at the actual learning algorithm that mixture of Gaussians clustering uses. From its name, you can tell that the Gaussian distribution plays a large role in mixture of Gaussians clustering. In fact, each cluster is defined by its own multivariate Gaussian distribution, which includes a mean vector and a covariance matrix. It is also assumed that each data point is generated by a mixture of these Gaussian distribution clusters. Therefore, the probability of a data point is equal to the weighted sum of its likelihood in each of the different cluster distributions. The weights, which we denote by pi, are called the mixing components, and they sum to 1. The mixing components can be thought of as the prior probability of any data point belonging to each cluster. But how do we use this setup for clustering? To do this, we compute the posterior distribution of each data point belonging to each cluster. We do this using Bayes' rule, where the likelihood is the likelihood of the data point in the Gaussian cluster distribution, and the prior is the mixing component of that distribution. Once we have computed this posterior distribution, we would know the probability of each data point belonging to each cluster. Therefore, this is the crucial quantity that we want to compute because it gives us our cluster assignments. Now that we know how mixture of Gaussians clustering works, let's compare it to k-means clustering. The obvious difference is that mixture of Gaussians clustering takes a probabilistic approach, whereas k-means does not. Another large difference between these clustering algorithms is the shape of the clusters that are learned. With k-means clustering, the shape of the cluster is determined by the distance function being used. With mixture of Gaussians clustering, the clusters can take the shape of any Gaussian distribution, which is somewhat more flexible. Furthermore, k-means creates hard clusters, which means that each data points belong to only one cluster. Mixture of Gaussians produces a distribution over cluster assignments, which means that a data point belongs to all clusters with different probabilities. Now let's take a look at the actual algorithm that is used to learn the posterior distributions that we are interested in. As you might have noticed, there are several parameters of this model that we need to learn. These are the mean vectors and covariance matrices for each Gaussian cluster and the matrix components pi. We need to learn these parameters from the data in order to compute the posterior. We will do this with the expectation maximization, or EM algorithm. The EM algorithm is an iterative algorithm that is often used for problems with hidden variables such as this one. It iterates between two steps, the E step and the M step, until convergence. A full explanation of the EM algorithm and why it works is beyond the scope of this course, but you can learn more about it in the following link. Finally, let's look at the pseudocode for the EM algorithm for mixture of Gaussians clustering. In the E step, we update the posterior distributions over cluster assignments, which depends on the hidden variables that we mentioned earlier. In the M step, we update the hidden variables given the posterior that was updated in the E step. The EM algorithm progresses by iteratively updating the posterior and hidden variables until convergence occurs, and we arrive at our final posterior distribution over assignments, which we can use for clustering. We have presented these update equations without proof, but if you are interested in their derivations, you can learn more in the following link. In this video, we have learned what mixture of Gaussians clustering is, how it compares to k-means clustering, and the algorithm it uses to learn its clusters. In the next video, we will actually implement mixture of Gaussians clustering in Scala and run it on an actual dataset. Welcome to the fourth video of this section. In the last video, we learned about the mixture of Gaussians clustering algorithm. We were going to implement what we learned in Scala. So in this video, we are going to implement the mixture of Gaussians clustering algorithm and cluster some actual data with it. We implement our mixture of Gaussians algorithm inside a class called Gaussian mixture, which takes two input arguments, the data matrix, which is a Breeze dense matrix object, and the number of clusters defined. We learned in the previous video that clusters are learned via the EM algorithm, where in the E step the posterior distribution over cluster assignments is updated, and in the M step, the hidden parameters are updated. We implement the E step as a method which takes two parameters, the cluster distributions themselves, which are a sequence of Breeze multivariate Gaussian objects, and also the mixing components pi, which are a sequence of doubles that sum to 1. In order to compute the posterior, we evaluate Bayes' rule, which means that we need the likelihood of each data point in each cluster. We do this by taking each row of the data matrix and evaluating data point for each cluster distribution. We then element-wise multiply these likelihoods with the priors for each cluster, which are the mixing components pi. Finally, we normalize by dividing each row by its sum to produce a proper distribution. What we are left with is a dense matrix object whose rows are the posterior probability of that data point being assigned to each cluster. Now let's take a look at the M-step method. This method takes the posterior matrix that was just computed in the E-step and also the clusters. If you remember from the previous slide, in the M-step we update the mean and covariance for each cluster distribution as well as the mixing components pi. Here we have implemented each update in a separate function. Let's start with the mean update function, which takes the posterior matrix as an input. If you remember from the previous video, the mean update for a cluster distribution is proportional to the sum over each data point's posterior probability of being assigned to that cluster multiplied by the data point itself. We do this by taking the columns of the posterior matrix and element-wise multiplying them with the data points and summing the result. We do this for each column of the posterior matrix, which corresponds to each cluster. Next, we perform the covariance matrix update in a very similar way, except following the update equations for the covariance matrices shown in the previous video. And finally, we update the mixing components in the pi update method in a similar way again. Here, the update equation is simple. For each cluster, we simply sum the assignment posterior probabilities for each data point and divide the result by the number of data points. The last thing we do in the M-step method is actually update the cluster distributions with the new means and covariances. Then we return them along with the new mixing components. Next, we will look at the cluster method, which actually connects the E-step and the M-step methods. First, the method randomly initializes the hidden parameters. The mean of each cluster is set to a random data point, and each covariance is set to the empirical covariance. The mixing components are also initialized randomly. Next, the E-step and the M-step are each evaluated until convergence occurs where the maximum number of iterations has been reached. Now let's cluster our New York 311 dataset with our mixture of Gaussians implementation. This is the same dataset we used to cluster with k-means. Let's choose 5 clusters and run the EM algorithm for 100 iterations. Let's run our code. The algorithm may take several minutes to converge, but once it does, the resulting clusters should look something like these. As you can see, the resulting clusters seem much more flexible in shape than those found through k-means cluster. In this video, we learned how to implement the mixture of Gaussians clustering algorithm in Scala. In the next video, we are going to dive into the unsupervised learning problem of dimensionality reduction, and specifically the PCA algorithm. In the last few videos, we looked at the clustering problem. In this video, we are going to shift our focus to another unsupervised learning problem, dimensionality reduction. First, we are going to remind ourselves what dimensionality reduction is and what it is used for. Then we are going to look at the principal components analysis algorithm in detail and understand how it performs this task. Let's revisit the dimensionality reduction problem definition. A dataset is comprised of data points, which are each vectors of features. The size of these vectors is the dimension of the dataset. For example, if you look at the dataset matrix that we have denoted X, the data points are the rows, and as you can see, each data point is a vector of length 3. Therefore, the dimension of the dataset is 3. Dataset Y, on the other hand, has a dimension of 2. The problem of dimensionality reduction is to transform a dataset into one with fewer dimensions while minimizing the loss of information. For example, transforming a dataset like X into a dataset like Y. There are several reasons why someone would want to do this. For one, it is often used as a pre-processing step to remove redundant features before applying a supervised learning algorithm. Also, since we can only visualize datasets in up to 3 dimensions, dimensionality reduction is often used to visualize data. Now let's take a look at the PCA algorithm. The general idea behind PCA is that it finds the directions of greatest variance in your dataset. Then the user chooses the p directions of largest variance, where p is smaller than d, the dimension of the dataset, and the original data is projected onto these p directions. And since these are the directions of greatest variance, the information lost by reducing dimensionality is minimal. In the graph below, the arrows represent the directions of greatest variance in the dataset, which is what PCA would find. Now let's take a look at the steps that PCA takes to actually do this. The first step is to normalize the data by subtracting the mean from each feature or column of the data matrix. Then the covariance matrix is computed for the normalized data matrix. Then the eigenvalues and eigenvectors are computed for the covariance matrix. Then the eigenvalues are ranked, and the p eigenvectors corresponding to the p largest eigenvalues are selected. Finally, the original dataset is projected onto a matrix composed of these p eigenvectors as columns. We end up with a transformed dataset with a dimensionality of p. Now that we've seen the steps that PCA takes, let's try to understand why it works. Firstly, let's recall the step where the eigenvalues and eigenvectors of the data covariance matrix are taken. In this step, the eigenvectors represent the directions in the data. The corresponding eigenvalues represent how much variance the data has in that direction. Therefore, taking the eigenvectors with the highest eigenvalues gives us the direction of greatest variance in our data. On the flip side, removing the directions of lowest variance will result in losing the least amount of information. For a more detailed explanation of PCA and why it works, check out this link. As a preview for the next video, we will see that PCA is such a popular algorithm, it is actually built into the Scala Breeze library that we've been using. In this video, we have learned what the PCA algorithm is and how it solves the problem of dimensionality reduction. In the next video, we will look at how to implement PCA in Scala. Welcome to the last video of this section. In the last video, we learned about the PCA algorithm and how it is used for the dimensionality reduction task. We are going to actually implement the PCA algorithm in Scala. In this video, we are not actually going to implement PCA from scratch, but rather use the version of PCA that is already implemented in Breeze. So the first thing we will look at is Breeze's PCA implementation, which we can view on GitHub through the following link. Then we are actually going to use this implementation to run PCA on our own dataset. So let's follow the link from the previous slide to view Breeze's PCA implementation. Here PCA is implemented as a class with two input parameters, the data matrix and the covariance matrix of the data. On line 36, we can see that the SVD algorithm is used to compute the eigenvalues and eigenvectors of the covariance matrix, which are already ranked by eigenvalues. This implementation uses a variable called scores, which projects the old dataset onto the eigenvectors to get the transformed dataset. Now let's run this implementation on our Boston housing dataset. We first create a small wrapper around Breeze's PCA implementation. Breeze's implementation does not compute the covariance matrix for us, so we must do that ourselves. Then we simply create a PCA object and supply it with the data and the covariance matrix. In this demonstration, we will look at the transformed lower dimensional data and the eigenvalues, which tell us the amount of variance explained by each new axis. Now let's finally run this on our Boston housing dataset. Here we instantiate our Breeze PCA wrapper by supplying it with our Boston housing dataset. When we run the code, we will print out the transformed data as well as the learned eigenvalues. Now let's run the code. If we look at the output, we can see that the first few eigenvalues are much larger than the remaining ones. This tells us that the variance can be explained well by the first few axes of the transformed data. Next, we print out the transformed data. If we wanted to, we could extract the first few columns of the transformed data, as we know from the eigenvalues that they explain most of the variance within the data. If we did this, we would be effectively reducing the dimensionality of the dataset. This is the last video in the unsupervised learning section of the course. In this section, we learned about two areas of unsupervised learning, clustering and dimensionality reduction. With clustering, we learned how to implement both the k-means clustering and mixture of Gaussians clustering algorithms in Scala. With dimensionality reduction, we learned how to implement the PCA algorithm in Scala. In the next section, we will learn about neural networks, which are becoming more and more popular in both academia and industry. Welcome to Section 5. In the previous section, we learned about unsupervised learning. In this section, we will learn about neural networks. In this first video, we will look at the feed-forward neural network model, which is also known as the multi-layer perceptron. In the next video, we will implement the feed-forward neural network model in Scala. Then we will learn about the restricted Boltzmann machine neural network model, which is used for unsupervised learning, and again, implement it in Scala. So let's begin the first topic of this section, the feed-forward neural network. In this video, we will first look at the neural unit and the activation function, which are concepts fundamental to neural networks. At that point, we will have all of the background necessary to look at the feed-forward neural network model and how to train it using the backpropagation algorithm. Let's get started with the neural unit. The neural unit is the simplest possible neural network model. The neural unit contains a weight vector W, and it takes an input vector x of the same size. The neural unit simply computes the inner product between the weight vector and the input vector. Then it takes the scalar result and passes it through an activation function. So what is an activation function? An activation function can be any nonlinear, easily differentiable function. The sigmoid function or the hyperbolic tangent function are common choices. The sigmoid function, which you can see plotted in the slide, is particularly convenient since it squashes any input between 0 and 1, allowing the result to be interpreted as a probability. Now let's move on to the feed-forward neural network model. The feed-forward neural network is made up of some number of layers. Each layer consists of some number of neural units. Subsequent layers are connected to each other by weights whose values must be learned. The first layer is known as the input layer and accepts an input vector, and the last layer is called the output layer and produces a final output prediction, which can be a vector or scalar value. The middle layers are known as the hidden layers. The forward pass refers to the process by which a feed-forward neural network produces an output prediction from an input vector. The process begins at the input layer. The input vector is multiplied by the weight matrix, which contains the weights between the input layer and the first hidden layer. The resulting vector is passed through the activation function in an element-wise manner. The result is then used as the input for the next layer of the network, and the process is repeated until the final layer is reached and the final predicted output is obtained. Now that we know how the forward pass works, the next problem is how to learn the required weight matrices. This is what is done in the training phase. There are many ways to train feed-forward neural networks. Perhaps the most common and effective method is stochastic gradient descent. The general stochastic gradient descent procedure is the following. First, all the weight matrices are randomly initialized. Then a data point is randomly sampled from the dataset. Then the forward pass is performed for the sampled input vector to get a prediction given the current weight values. Then, given the prediction error, the error gradients are computed for each weight in the network. This computation is performed using the backpropagation algorithm, which we will describe next. Finally, each weight is moved a step size in the direction of its error gradient. This sampling and update process is repeated until convergence. Finally, let's look at the backpropagation algorithm, which was used in the stochastic gradient descent procedure to compute the error gradients with respect to each weight in the network, given the prediction error from the forward pass's prediction. In the case of a feed-forward network for binary classification, the prediction error is simply the difference between the predicted output and the actual output. Let's call this delta k for a network with k layers. The error gradient for the weights connected to the last layer of the network can be obtained by taking the inner product between delta k and the output of the previous layer, which was computed during the forward pass. The next step is to compute the delta for the previous layer, k-1. This is given by the following formula, which is a function of the layer weights and also the deltas for layer k. This procedure is then continued backwards through the network until all the error gradients have been computed. Notice how we are reusing previous computations, making this a dynamic programming algorithm and thus much more efficient than calculating each gradient in a brute force fashion. If you'd like to learn more about the backpropagation algorithm and neural networks in general, I recommend the third chapter of Alex Graves' thesis, which you can read using this link. In this video, we learned about feed-forward neural networks, including how they are trained with stochastic gradient descent and the backpropagation algorithm. In the next video, we will actually implement the feed-forward neural network in Scala and run it on a real dataset. Welcome to the second video of this section. In the previous video, we learned about the feed-forward neural network model. In this video, we are actually going to implement it in Scala. Specifically, in this video, we are going to step through the implementation of the feed-forward neural network in Scala. Then, we are going to run it on the simple XOR dataset example. The core of the Scala implementation is the train method, which takes 6 input arguments. The first is the dataset itself, which is a sequence of training example objects, which is a case class consisting of the inputs and the outputs, both of which are dense matrix objects. The second input argument is the layer dimensions, which is a sequence of integers whose length is the number of layers in the network and whose element values are the size of the corresponding layers. The next two arguments are the activation function and the derivative of the activation function. The final two arguments are the learning rate and the number of epochs, which are the parameters of the stochastic gradient descent procedure. The first computation that is performed in the train method is called initialize weights, which initializes the weight matrices for each layer in the network. Inside the method, we simply iterate through the layer dimension sequence with a fold left, and initialize random matrices of the appropriate size and update the accumulator. The output is a sequence of random matrices representing the initial weights of each layer. The next step in the train method is to actually begin the stochastic gradient descent procedure. Here we iterate through each example in the dataset over several epochs and perform the following 3 steps: the forward pass, the backward pass, and the weight update. The forward pass is performed in the forward pass method. This method takes 3 input arguments: the input to the network, the current values of the layer weight matrices, and the activation function. Here again, we use a fold left to iterate through the layer weights, and at each iteration, we multiply the input by the appropriate weight matrix, and pass the result through the activation function, and pass the new input to the next layer. We must persist these inputs because they will be used in the backpropagation step. The backpropagation algorithm is performed in the backward pass method. This method takes 6 arguments: the activations from the forward pass, the current value of the layer weight matrices, the predicted and actual outputs, the activation function, and also the derivative of the activation function. In this method, we first compute the prediction error, then we iterate through the layer activations, each time computing the layer gradients and deltas that were described in the previous video. This method eventually returns the error gradients that will be used to actually update the weight values. This update is then performed in the SGD method. This method takes 3 arguments: the current values of the layer weights, the gradients computed from the backward pass method, and the learning rate parameter. In this method, we simply update the layer weights by adding the corresponding gradient scaled by the learning rate. We do this by zipping the weights and gradients together, then using a map function to perform the update. Now let's train our own neural network model based on the XOR function. The XOR function is a nonlinear function which takes 2-dimensional binary valued inputs and produces scalar outputs, where the output is 0 if the input elements are the same and 1 if they are different. This function is typically difficult to learn since it is not linearly separable. Here we choose the sigmoid function as our activation function, and we will use a learning rate of 0.1. Let's instantiate our feed-forward neural network model and call the train method with our XOR dataset and give it the dimensions of 2, 2, and 1 and run it for 5,000 epochs. If we run the code, we can see that at the end of the process, the predictions are almost identical to what the actual XOR outputs should be. Thus, we have trained a neural network to learn the XOR function. In this video, we learn how to implement a feed-forward neural network in Scala. In the next video, we will learn about a new kind of neural network model called a restricted Boltzmann machine, which is typically used for unsupervised learning. Welcome to the third video of this section. In the previous videos, we looked at feed-forward neural networks applied to the supervised learning problem. In this video, we will look at a different class of neural networks called restricted Boltzmann machines, or RBMs, which will be applied to the unsupervised learning problem. In the first part of this video, we will learn about the structure of restricted Boltzmann machines and how they address the unsupervised learning problem. After that, we will learn how to actually train a restricted Boltzmann machine on a dataset. As we learned earlier, a restricted Boltzmann machine is a neural network model that is typically used for unsupervised learning tasks like clustering and dimensionality reduction. In terms of network structure, an RBM is actually quite simple. There are only two layers, the visible layer and the hidden layer. Each visible neural unit is connected to every other hidden neural unit via a weight, creating a bipartite graph. So given a vector of visible units, the RBM generates a vector of hidden units. The restricted part of a restricted Boltzmann machine comes from the fact that there are no connections between visible units or between hidden units, only between visible and hidden units. Another important property of an RBM is the fact that it only works with binary valued visible units, and it also generates binary valued hidden units. However, there are variants of the RBM that can accept different kinds of inputs, like the replicated softmax model. The hidden units are generated from the input visible units in a very similar way to the feed-forward neural network. Just like in the feed-forward neural network, the input vector is multiplied by the weight matrix, and then the resulting vector is passed through the sigmoid activation function, which pushes each vector element to either 0 or 1, resulting in a binary valued output vector. This output vector represents the hidden units. And similarly, the input can be reconstructed from the output hidden units by applying the same process in reverse. Specifically, we multiply the weight matrix by the hidden output vector on the opposite side, and pass the result through the sigmoid function again, giving us a reconstruction of the binary valued input vector. If the weights have been trained correctly, this reconstruction should be close to the original input vector. Now that we know how an RBM works, we must learn how to train the weights. The network weights are learned via an algorithm called contrastive divergence. The derivation of the contrastive divergence algorithm is beyond the scope of this video, but you can study that yourself if you follow this link. However, we will cover the contrastive divergence procedure. It is an iterative algorithm that is very similar to the stochastic gradient descent algorithm that we learned about in the feed-forward neural network videos. We start with a randomly initialized weight matrix. The algorithm begins by sampling a data point V from the dataset. Then we perform a forward pass and generate the corresponding network hidden vector H. Then we compute what is known as the positive gradient, which is the outer product of the input vector and the hidden vector, which results in a matrix. Then, given the hidden vector that was just generated, we perform a backwards pass and generate a reconstruction of the inputs V'. Then we perform a second forward pass. However, this time we begin with a reconstructed input vector rather than the actual input vector, which gives us a reconstruction of the hidden vector H'. Then we compute what is known as the negative gradient, which is the outer product of the visible reconstruction and the hidden reconstruction. Then we finally update the weight matrix by moving it a step size in the direction of the difference between the positive gradient and the negative gradient. This process is then repeated, each time sampling a new data point from the dataset. Eventually, we should converge to the optimal weight matrix. In this video, we learned what restricted Boltzmann machines are and how they are trained. In the next video, we will actually implement a restricted Boltzmann machine in Scala and train it on an actual dataset. Welcome to the last video of this section. In the previous video, we studied some of the theory behind restricted Boltzmann machines, including what they are used for and how they are trained. In this video, we are actually going to implement what we learned about restricted Boltzmann machines in the previous video in Scala. Specifically, in this video, we are going to implement the RBM model in Scala, including the contrastive divergence algorithm for training. Then we are going to demo our implementation with some actual data. Let's go to the IDE to look at the Scala RBM implementation. Let's first look at the contrastive divergence method, which takes 4 input arguments: the visible units, the weight matrix, as well as the hidden and visible bias units. From the previous video, we know that the first step of the contrastive divergence algorithm is to generate the hidden unit output from the visibles. We do this in the code by multiplying the weights by the visibles, adding the hidden bias vector, and passing the result through the sigmoid. We then pass the result through a function called binarize, which sets each element of the output vector to 1 if it is greater than a normally distributed random number between 0 and 1, and 0 otherwise. According to Jeffrey Hinton, this is a heuristic that tends to improve training performance. The next step in the contrastive divergence algorithm is to reconstruct the visible units from the hidden units. We do this by multiplying the binary hidden output by the transposed weight matrix, adding the visible bias, then passing the result through the sigmoid function. At this point, we can compute the positive gradient, which is just the outer product between the hidden probabilities and the visible units. Then, we reconstruct the hidden outputs from the reconstructed visible outputs in the same way. Then we can compute the negative gradient, which is the outer product between the reconstructed hidden probabilities and the reconstructed visible units. Finally, we compute the weight gradients, which is just the positive gradient minus the negative gradient. The function returns the gradients for the weight matrix and the biases. It also returns the reconstruction error, which is the sum of squares difference between the reconstructed visible units and the actual visible units. Next, let's look at the learn function, which calls the contrastive divergence function. It takes 4 arguments: the input data, the number of hidden units, the batch size for learning, and the learning rate. The weight matrix is initialized randomly from samples from a normal distribution centered around 0. The bias units can be initialized to 0. Next, we divide the input data into a number of mini-batches using Scala's grouped function. We then traverse the mini-batches sequentially, calling the contrastive divergence method on each one. We then update the weight matrix and biases by moving them a step size in the direction determined by the contrastive divergence algorithm. Notice that we also have another term in the update equation, where we add a fraction of the last update to the current update. This is called momentum, and it often improves convergence in neural networks. We perform these updates over several passes over the dataset, which we call epochs. Let's now run the code on a toy binary value dataset of a few examples. Let's call the learn function on this dataset with a mini batch size of 6 and a learning rate of 0.05. Let's run the code and plot the reconstruction error across epochs using WISP. As you can see, the reconstruction error is decreasing, which means that the hidden unit output is learning how to reconstruct the inputs. In this video, we learned how to implement the restricted Boltzmann machine neural network model in Scala. We have finished the neural network section of this course. In this section, we learned about the feed-forward neural network and the restricted Boltzmann machine models, and implemented them both in Scala. In the next video, we will begin a new section called Other Scala Frameworks for Machine Learning. Welcome to section 6. In the previous section, we looked at neural networks. In this section, we will look at some other Scala frameworks for machine learning. The first framework that we will be looking at in this section is the Akka actor framework, which is a popular tool for dealing with concurrent programming in Scala. In this video, we will first define the concurrency problem. Then we will look at some synchronous solutions to the problem, and then look at the Akka actor model, which provides an asynchronous solution. Then finally, we will look at some basics regarding Akka actor creation. In modern multi-core CPUs, multiple threads can perform tasks within the same program, which greatly increases performance. However, when you have multiple threads working within the same program, they are all reading and writing to the same memory. The variables that interact with these threads are called the shared mutable state. This shared mutable state can cause a lot of problems. Consider the case when thread A reads the value of a particular state at time t, and then thread B changes that value. At this point, it is difficult to predict which value thread A holds. It is dependent upon the underlying CPU thread scheduling algorithm. This is called a race condition and should be avoided. Consider the following example where two threads interact with a shared integer variable. At first, both threads read the correct value of 0. Then each thread increments the value it read. The problem arises when thread 1 writes the updated variable, which is different from the value that thread 2 initially read. Thread 2 then writes its own incremented value based on the outdated value of the shared variable. So in the end, we end up with the incorrect value of 1 instead of the correct value of 2. One solution to the concurrency problem is to synchronize your threads, meaning have the threads communicate with each other so that each has a designated time to interact with the shared mutable state. However, the synchronous solution brings with it a lot of problems, such as deadlocks, inefficient use of threads, and the corresponding code is generally error-prone and difficult to read. The Akka actor model, on the other hand, is asynchronous. In this model, the shared mutable state is encapsulated by what is known as an actor. Actors communicate with each other by passing messages which are generally used to read or write to the actor's mutable state. This message passing is asynchronous, meaning that the actor who sent the message does not have to wait for an acknowledgement from the recipient actor, which leaves it free to do other work. When an actor receives a message, it is put in its mailbox and they are processed one by one. Another important property of actors is that actors are allowed to create their own child actors. Now let's take a look at a very simple Akka actor example. The first thing you need to do is include the Akka Maven dependency in your build file. After you have the Akka dependency, you can create an actor. An actor is a Scala class that extends the actor trait, which comes from the Akka dependency you just added. The actor trait has an abstract receive method, which you must implement in your class. The receive method is where you define what happens when your actor receives a message. A message is typically just a Scala case class or case object. They are conventionally defined in a companion object to your actor class. Here you can see two messages, greeting and goodbye. You can also see that the greeting message has a from field, which shows that messages can actually pass values as well. We define what our actor does when it receives these messages via Scala's pattern matching capabilities. In this example, we are just logging that a message was received, but in theory, you can do almost anything when you receive a message. In this video, we learned about the concurrency problem and the asynchronous solution that is provided by the Akka actor model. In the next video, we will actually implement a machine learning algorithm we have seen before, the k-nearest neighbors algorithm, in a multi-threaded fashion using Akka. Welcome to the second video of this section. In the last video, we learned about the Akka actor model for concurrent programming. In this video, we are going to use the Akka actor model to implement the k-nearest neighbors algorithm in Scala. The first thing we are going to do is figure out how the k-nearest neighbors algorithm can use multi-threading. Once we've figured that out, we're going to move over to the IDE and actually implement it in Scala. If you remember back to the previous video on the k-nearest neighbors classification algorithm, you will remember that it is conceptually quite simple. Given a data point whose class you wish to predict, you search your training dataset for its k-nearest neighbors according to some distance measure. The predicted class is then the most common class amongst the k-nearest neighbors. But if the dataset is large, performing a linear search can be slow. One way to optimize this algorithm is to partition the training set and perform the search on each partition simultaneously, with each partition returning its k-nearest neighbors. Finally, you would merge the results from each partition and then sort them in order to get the overall k-nearest neighbors. This optimization involves multiple threads working at the same time and therefore can be implemented with the Akka actor model. In terms of actors, you would need one master actor that partitions the data and creates a child actor for each. At prediction time, the master actor would send a message to each of the child partition actors containing the data point whose class needs to be predicted. Once received, this message triggers the actors to perform a k-nearest neighbors search on their partition of the dataset and return the result back to the master actor. Once the master actor has received the results from all of the children, it merges them and finds the overall k-nearest neighbors and computes the final prediction. Let's start by looking at the master actor that we will call NN master. As you can see, it extends the actor trait. It takes 5 input arguments: the inputs, the outputs, the k parameter, the distance function, and the number of partitions that the actor will create. The first thing we do is partition the inputs and outputs. We do this with Scala's built-in group function, where the group sizes are the total size of the training set divided by the number of partitions. The next thing we do is create a child actor for each partition. We first create an empty array of act objects to store them. Then we create actors for each of the partitions with the context.actorOf command, and then store them in this array. The child actors are called NN-slave, and we will look more closely at these next. Like every actor, NN-master must implement a receive method. NN-master can receive a query input message, which contains the data point whose class must be predicted. Here we pass this message to each of the partition actors that we just created via the exclamation point symbol, which is an Akka DSL. Once this is done, NN-master switches to a waiting state, where it waits for the partition actors to return their results. In this state, it can receive top k messages, which contain the k-nearest neighbors of the partition actor identified by the ID field. Once all the partition actors have sent their results, we simply sort them by distance and take the top k neighbors, and finally compute the predicted class in the exact same way as our previous k-nearest neighbors implementation. And finally, it sends the prediction back to whatever actor created NN-master using context.parent. Finally, let's take a look at the partition child actors that we created in NN-master. We have called these NN-slave, and notice how they also extend the actor trait. They take 5 arguments: a unique ID to identify them, the input and output training data of their partition, the k parameter, and the distance function. Again, like every actor, NN-slave must implement its receive function. The NN-slave actor can receive the query input message that the NN-master actor sends it. Once received, it computes the k-nearest neighbors from its partition data in the exact same way as our original k-nearest neighbors implementation. When that has finished, it sends the results back to the NN-master actor wrapped in the top k message. Also notice here how we can automatically refer to the actor that originally sent the message by using the sender function. Finally, let's run this implementation with our ionosphere dataset for classification. Let's first define our distance function as Euclidean distance as we have done before. Then we create an instance of the NN-master actor, supplying it with our dataset of inputs and outputs, our k parameter, our distance function, and the number of partitions to use. Here we use 4 partitions, and we use a k parameter of 4. Next, let's send a data point to the NN-master actor whose correct class is G. In our receive method, we will receive the final prediction message from NN-master and print it. We will kick off this entire process with a driver object which creates the actor context. Let's run the code. When we run the code, we can see the various logging statements that we have included throughout the process to make sure everything is working. And finally, we see the correct class of G is printed as the prediction. Congratulations! We just implemented a multi-threaded version of the k-nearest neighbors algorithm with Akka. In the next video, we will introduce another interesting Scala framework that can be used for machine learning called Apache Spark. In the last couple of videos, we looked at the Akka framework. In this video, we will introduce another Scala framework that can be used for machine learning purposes called Apache Spark. At the beginning of this video, we will get familiar with the fundamentals of Spark by defining what it is and what it is used for. Then we will look at Spark's RDDs, Spark's fundamental data structure. Then finally, we will take a look at MLlib, the machine learning library for Spark. At a high level, Spark is a framework for parallel cluster computing written in Scala. Spark's key feature, which differentiates it from its predecessors like Hadoop and Scalding, is its ability to keep data in memory and limit data transfer. The implications of this is that disk I/O is reduced, which greatly speeds up parallel computation. Also, it allows for easier parallel processing of iterative algorithms. Many algorithms in machine learning are iterative in nature, which makes Spark a good fit for machine learning. The fundamental unit of computation in Spark is called a resilient distributed dataset, or RDD. An RDD is a linear data structure like an array or a list, with the difference being that its contents is distributed across the machines in the cluster. Therefore, all operations performed in an RDD are done in parallel. The types of operations that can be performed on an RDD can be put into two categories: transformations and actions. Transformations are operations that are performed on an RDD that produce another RDD. These are operations like maps, filters, and flat maps. Actions are operations that are performed on an RDD that return a local value to the driver machine in the cluster. These are operations like collect, reduce, and count. Now let's take a look at an example Spark application. In this example, suppose you have a very large text file and you want to perform a parallel word count. Let's go through each line in this example. In the first line, we read the text file from HDFS into an RDD of strings. Here, SC refers to the Spark context. We then apply the flat map transformation to the text file RDD with a function that splits on white space into words. Therefore, the result is an RDD of word strings. Then we apply a map transformation and transform each word to a tuple where the first element is the word and the second is 1. Then we apply a reduce by key with an addition function. Here the key is the first element in the tuple, which in our case is the word. So what reduce by key does is it aggregates elements of the RDD with the same word and sums the corresponding values. Since the corresponding values are 1, this is equivalent to a word count. Now that we have some idea of what Spark is and how it works, let's take a brief look at the MLlib library. MLlib is a library that includes Spark implementations of many common machine learning algorithms like the ones that we have seen in this course. A common question that is asked is when to use a Spark implementation of a particular machine learning algorithm versus using a standard Scala implementation. There's no cut and dry rule to tell you when a machine learning algorithm should be parallelized, but there are a few potential indicators that your machine learning algorithms might benefit from parallelization. One indicator is if your dataset is so large that your Scala implementation is running out of memory. In this case, your implementation might benefit from the memory advantages that cluster computing provides. Another indicator is when your algorithm takes a prohibitively long time to finish. In this case, parallelization might speed things up. On the other hand, parallel computation really only has a benefit when your dataset is large. If it is not large enough, the overhead required for parallelization might actually end up slowing down your implementation. In this video, we introduced Apache Spark. We learned what it is and how it works, as well as its fundamental data structure, the RDD. At the end of this video, we introduced MLlib, the Spark machine learning library. Welcome to the fourth video of this section. In the last video, we got introduced to Spark, and at the end we touched on MLlib, Spark's machine learning library. In this video, we are going to actually build a Spark application that uses MLlib. The first thing we need to do is add the Spark core and Spark MLlib dependencies to our build file. Now let's move on to our Spark linear regression application. As a dataset, we will be using the Boston housing price dataset that we used for our original linear regression example. The first thing that is done in any Spark application is to define the Spark context. First, we must create a Spark instance in which we set the Spark app name and also the location of the master node. In this case, we have set the master to local, which indicates a standalone Spark implementation on a single computer. The 2 in the square brackets indicates that 2 threads will be used. Once the Spark conf is defined, we can define the Spark context. We must also put the training data in a format that MLlib can understand. In order to do this, we must represent each training example as a labeled point object, whose first field is the example output, and whose second field is the input feature vector, which is represented as an MLlib vector. The next step is to parallelize the training dataset. We do this by calling the parallelize method from the Spark context, which transforms it into an RDD of training examples. Next, we can actually train our linear regression model. We do this by using MLlib's linear regression with SGD object and call its train method. The method takes 3 arguments: the training data RDD, as well as the step size and maximum number of iterations to use. The output of the train function is our linear regression model. We can then make predictions using the model we just trained. Here we iterate through the training data and predict each output using the model's predict method. Let's run this Spark application inside the terminal. Once the Spark application has finished running, and we look through the Spark logs, we can see our final training error that we arrived at. This has been the last video in section 6 of this course. In this section, we learned about the Akka actor model for concurrency, which we then used to create a multi-threaded k-nearest neighbors implementation. Then we learned about the Apache Spark framework for distributed computation, and specifically its MLlib library, which we used to implement linear regression in Spark. This is also the last video of the course. Let's look back on what we have learned. In the first section, we were introduced to the Scala programming language, where we learned about functional combinators and traits, classes, and objects. Then in section 2, we learned about exploratory data analysis, where we covered concepts such as descriptive statistics and visualizations. Then in section 3, we dove into supervised learning, where we learned about and implemented several regression and classification algorithms. Then we looked at unsupervised learning in section 4, where we studied clustering and dimensionality reduction. Then in section 5, we covered neural networks and implemented 2 neural network models. Finally, in this section, we looked at 2 other Scala frameworks for machine learning, Akka and Apache Spark.